Hello and welcome back once again. In the previous lecture, we started discussing about the fatigue behavior of metal matrix composites. So, if you recall, we have spoken about stress controlled fatigue and strain controlled fatigue. So, with regard to fatigue of MMCs, let us talk about first the stress controlled fatigue behavior. So, when stress controlled fatigue experiments are conducted on metal matrix composites, it has been generally found that the fatigue lives of discontinuously reinforced MMCs are higher compared to the unreinforced metals. Okay, so that's the first observation that you can make about the stress controlled fatigue behavior of discontinuously reinforced MMCs under stress controlled fatigue. This can be shown graphically also if we take the stable loops that develop during stress controlled fatigue experiments. For example, we can take this aluminium copper alloy and their composites, and if you look at the stable loops under stress controlled fatigue for such material, it can be shown schematically as follows. Okay, so the dotted line represents the unreinforced metal and the solid line is for the composite, and this is at low stress. So here you can see that at a given cyclic stress, that is delta sigma composite is equal to delta sigma metal, the total strain in the composite is lower, that is delta epsilon composite is lower than delta epsilon metal. Okay, so here this delta epsilon is basically the total strain. Okay, this is true at high stress also. So if you look at the loops at the high stress, it may look like this for this particular material, aluminium copper alloy and its composite. So this one is for the composite, and this is the dotted one is for the unreinforced matrix. So here also you can see that at a given cyclic stress, the strain in the composite is much lower. Okay. So if you look at the plastic strain, for example, in the composite, this is the plastic strain. Which is much higher compared to that in the unreinforced matrix. So that you can see from here itself. This is the plastic strain in the unreinforced metal or alloy at the same cyclic stress. Okay. So here also you can see that at a given cyclic stress, the total strain in the composite is lower compared to that in the unreinforced metal. And the plastic strain in the composite is also lower compared to that in the unreinforced metallic matrix. Okay. It can be explained as follows. So basically there are two primary factors responsible for this kind of behavior in the composite. So the higher fatigue life in the composite can be attributed to these two primary factors. One is a reduced elastic strain due to the higher modulus of the composite. And secondly, a reduced plastic strain resulting from an increase in the work hardening of the composite. We have already talked about this before as to how the work hardening in the composite is higher compared to that in the unreinforced metallic matrix. So in stress controlled fatigue, these are the two primary factors responsible for higher fatigue life in the metal matrix composite. So you can see that the superior fatigue resistance of the composite basically results from the lower total strain, but more importantly, the lower plastic strain at which it is cycled. Okay. This basically results in a delayed crack initiation, and as a result of that, the number of cycles to failure will be much higher, resulting in a better fatigue resistance. So now let us also talk about the effect of the mean stress or the stress ratio. So if you recall, while discussing about general fatigue, we have seen that the mean stress or the stress ratio will also have an influence on the fatigue behavior. So the mean stress sigma m is given as sigma maximum plus sigma minimum by 2, and the stress ratio R is the ratio of sigma minimum and sigma maximum. Okay, so we have seen that depending on the value of R or sigma m, the fatigue life can change. Okay, so let us see, when we talk about the fatigue behavior of metal matrix composite, how this factor will play a role. Okay, so we will again take an example of a particular composite. So let us take this composite 2080 aluminium 15% silicon carbide particle. Okay, so let us see how do the fatigue SN curves look like for this particular material under different stress ratios. So let's say we are talking about a stress ratio of -1, that is the fully reversed loading condition. And if you look at the fatigue curves for the composite and the unreinforced alloy in that condition, it will look like this. So here maximum stress is plotted against number of cycles to failure. And now if you look at the plots of the composite and the unreinforced matrix, they look like this. Okay, so this is how the fatigue curves will look like for these two materials, the unreinforced 2080 alloy and its composite reinforced with 15% silicon carbide particles. So there are few things that can be noted here for this condition when it is fully reversed, that is R is equal to -1. So the first thing that you can note here is the fact that the composite is having a better fatigue life compared to the unreinforced alloy, as you could see from here. Okay. But the important thing to note here is that the differences in the fatigue lives between the composite and the unreinforced alloy are more pronounced at intermediate and low stresses depending on the stress ratio. Okay. All right. So that is what you can see over here, right? This portion is having the greatest difference, right? And at high stresses, the differences are minimized, right? And the fatigue lives of the composite and the unreinforced alloy are generally similar. So that's what you can see at the high stress levels, that is on the right hand side corner over here at this part. These two curves kind of march. Okay. So that indicates that at high stress levels, their fatigue lives are not very different. And also under fully reversed condition, the maximum gain in the fatigue life is obtained in the intermediate stresses. So for R equals to -1, the maximum gain in the fatigue life is in the intermediate stress levels. That is what you can see here that I showed in the shaded portion over here. The difference is greatest here in this portion around the intermediate stresses when R is equal to -1 or when the load is fully reversed. This can be explained as follows. So we have seen before that from a continuum theory perspective, the proportional limit of the composite is lower than that of the unreinforced matrix. And this has a bearing on the fatigue property of the material, particularly when the load is fully reversed. So under such conditions, at low stresses, the amount of plastic strain is generally low and the fatigue life will correlate better with the elastic strain. So that is clear. When the stresses are low, the strains will also be low, so it will be kind of elastic strain in the material. However, you can see an impact of this lower proportional limit in the sense that, at least theoretically, at low stress levels, the average plastic strain in the composite may be greater than what is experienced by the unreinforced material at the same stress. Okay, so this is an impact of the lower proportional limit that you can see over here on the fatigue property of the material. Okay, so when you go towards a stress condition when the mean stress is positive, the plastic deformation will occur in the first cycle, but in subsequent cycling it will be generally elastic. But because the elastic strains and thus the total strain also, because the total strain is a summation of elastic and plastic strain, are lower in the composite, improvements in the fatigue life are observed for composite materials. Okay, and that is what you can see from this plot over here when R is equal to zero point 0.1, which is positive. So here also the maximum stress is plotted against number of cycles n, and this is under condition of R equals to 0.1. Okay, so now if you look at the fatigue behavior of the composite and the unreinforced alloy, it will look like this. Okay, so the upper one is for the composite and the lower one is for the unreinforced alloy. Okay, so here you can see that the fatigue life of the composite is higher. As I said before, or the fatigue resistance for the composite is better. This is because of the fact that the total strength in the composite is lower, right? And the other thing that you can note from here is that under such loading conditions, when R is positive or near zero, like for example in this case R is 0.1, the most pronounced improvement in the fatigue life for the composite is obtained at lower stresses. That's what you see from here when you look at these curves of the composite and the alloy. You can see that the difference in the fatigue lives is more pronounced at the lower stress levels. Okay. But when you talk about the fully reversed condition, first of all, you can see that stable stress strain loops form and the higher plastic strain in the composite is retained with subsequent cycling. Okay. So therefore, under fully reversed loading at low stresses, the damage resulting from the plastic deformation may be greater in the composite compared to that in the unreinforced matrix. Okay. So going back to this fully reversed condition, we can see that the plastic strain in the composite is higher due to theoretically lower proportional limit. Okay. And as a result of that, the deformation or damage resulting from the subsequent stress cycles is more in the composite, as I said. Okay. So that is why at fully reversed loading condition, we can see that even at lower stresses, due to the lower proportional limit of the composite, at least theoretically, plastic strain can be still higher, and therefore the improvement in the fatigue life over the unreinforced alloy is insignificant. Okay. So that's what you can see, if you go towards the lower stress or towards the right corner of this plot, you see that these two curves, these two plots kind of merge with each other, right? So there is hardly any difference in the fatigue life of these two materials. Lower stress or high cycle fatigue behavior of the composite and the unreinforced alloy is very similar. Okay. Now you can also see that at the higher stress levels around this corner, here also the fatigue behavior of the composite and the unreinforced alloy is not very different. The difference between the fatigue lives is not so significant. Okay. So this can be probably attributed to the ductility of the composite material. So generally it has been found that the cyclic ductility of the composite is lower compared to the unreinforced matrix material. Okay. So this lack of ductility of the composite will actually limit the plastic strain and hence the number of cycles that can be accumulated prior to fracture. Okay. So because of this, the number of cycles that can be accumulated in the low cycle fatigue region is limited. Okay. And therefore, at high stresses, although the plastic strains are lower in the composite, due to the lack of cyclic ductility, the resistance to the cyclic strain is low, and this leads to the convergence of the fatigue lives, as you could see. Okay. So there are two competing factors here. One is the low plastic strain, which will improve the fatigue life or reduce the fatigue damage in the material. But on the other hand, the ductility in the composite is lower, which will actually limit the strain to fracture and lead to an early fracture, right? So because of these two competing factors at high stresses, the fatigue lives of the composite and the unreinforced alloy are very similar to each other. The difference in the fatigue lives is not that significant. Okay. So this was all about the stress controlled fatigue behavior of metal matrix composites. And with that, we come to the end of this lecture. But there will be more on this topic when I come back. Until then, goodbye.